Imagine this. You're driving down a straight road. Let's say you pass a sign at exactly 2 p.m. and then another sign 10 miles later at exactly 2:10 p.m. If I had asked you how fast you were going, you'd probably say something like 10 miles in 10 minutes, so that means 60 miles per hour. You see, that's your average over those 10 minutes. But now imagine this. You're watching your speedometer, and at exactly 2:05 p.m., it says that you're traveling at 72 miles per hour. You see, that's not your average anymore. That's your instantaneous speed. It tells you exactly how fast you're going right now. You see, this is what a derivative is. It's the mathematical version of your speedometer. It doesn't look at how far you traveled. It just looks at how your position is changing at this exact second. Now, let's look at a simple equation. This equation is y equals x squared. You may know it as a parabola. For this case, the x is time and the y is position. Treat this parabola like the car problem. At x equals 0, the car is at y equals 0. And at x equals 2, the car is at y equals 4. Let's say we want to find the rate of change of the parabola at x equals 0.5. Looking at the average, we might say the parabola has a rate of change of 2. However, when we actually look at the parabola, it's not linear, so the rate of change cannot be constant. For this, we need to take the derivative. Before I show you a way to do this, try coming up with a solution yourself. Here's a hint. The derivative is a line that only touches the function once, meaning you're looking for a line that doesn't pierce through the function, touching 2 points. Okay, if you think you have the answer, make sure to put it in the comments below. So, if we look at this graph here, drawing a line from 0 to 2 gives us our average rate of change, 2. But we want the slope at 0.5. So let's increase the bottom intersection point from x equals 0 to x equals 0.5. Now we have a line from 0.5 to 2. This gives us a rate of change of 2.5. Since the derivative only touches a function once, that means that the line can only hit the function at x equals 0.5. And it can't hit it at 2. But how would we do this? Well, let's think about the point-slope form for a second. You should be pretty familiar with this form. In this case, h is 0.5 and k is f of 0.5, so 0.25. But what we really care about is m. You see, the m is the slope of the tangent line, which is also the derivative. Normally, we know m as y1 minus y2 over x1 minus x2. However, if we want y1 and y2 to be the same, this would give us 0 over 0, which cannot be evaluated. Thus, we have to refactor the equation. Since we know y1 is just f of x1 and y2 is just f of x2, we can rewrite the equation like so. For the sake of simplicity, we will write x1 in terms of x2 so we can simplify to a single variable and a constant value. To avoid confusion, we will use n. However, the equation that most mathematicians use uses h instead. This shouldn't really matter too much. Now, let's see what happens when we make n closer and closer to 0. Keep in mind that this will make y1 and y2 closer to each other, and x1 and x2 closer as well, solving our initial problem. As we can see, the slope of the line seems to be converging to a specific number as n gets closer and closer to 0. At n equals 1, the slope is 2. At n equals 0.1, the slope is 1.1. At n equals 0.01, the slope is 1.01. And at n equals 0.001, the slope is 1.001. We can say that as n approaches 0, the slope approaches 1. This means that at 0.5, the slope of the tangent line is 1, meaning the derivative is 0.5. In mathematical terms, we say that with the limit of n approaching 0, m approaches 1. This also works from the negative side. In fact, checking both sides, both positive and negative, is crucial for odd cases with discontinuities in the graph. However, with continuous and smooth functions, that shouldn't matter too much. Well, that's great. We just found the derivative. However, let's see what happens when we plug in x squared for f of x. Now we have this expression which can be evaluated. Pause the video now to see if you can do it on your own. You should still get the same answer, which is 1. Alright, hopefully you still got the same answer when simplifying. Make sure to leave a comment if you didn't and I can help you figure out why. Anyways, that's all for today's video. For the next video, we'll go over many other advanced techniques to take derivatives. This is just the beginning of your calculus journey. Make sure to like and subscribe as it helps me a lot. Thanks for watching.